Hi everyone, welcome to the continuation of lecture number 4 on waves, but only for the calc-based physics students, okay? I'm going to go over some mathematics which explains some of the phenomena that we discussed in the other lecture, which did not have any calculus in it. But because these equations in this math has calculus, it's only for the calc-based physics, okay? And what I'm going to do is I'm going to describe this equation, the wave equation, which talks about how the coupled oscillators in a medium give rise to wave phenomenon, okay? And even so, I'm not going to go very deep into this mathematics because it's probably too much even for like for a second semester physics course, but I want to go into it enough that you get some understanding of what's going on, especially this business of coupled oscillators, coupled harmonic oscillators giving rise to the wave equation, okay, or giving rise to wave phenomenon. All right, so well, let's start. Okay, so just let me remind you what a wave is. A wave is a collective phenomenon. It's not just one object doing its own thing, like an oscillator oscillating back and forth. It's many oscillators together, and these oscillators are cooperating in such a way as to give this wave phenomenon, okay? And the way the oscillators do that is, one oscillator might be moving up and down, but it exerts a force on its neighbor. And so when it moves up, it pulls the other one up. It pulls its neighbor up, okay? And when it comes down, it pulls its neighbor down. Now, of course, that neighbor has another neighbor, which also it influences, and so on down the line. And that's how this wave phenomenon propagates through the medium, okay? And all of this is actually described out of Newton's laws, but you might wonder, how in the world can I use Newton's laws to describe, this infinity of harmonic oscillators that are all coupled with one another? Okay, so I'm going to try to give you some insight into that in this lecture. Now, I also want to do this, introduce you to this mathematics, because some of you are chemistry majors, and if you go on to PChem, you'll be looking at Schrodinger's equation, and which is for quantum mechanics, and some of this translates into that, okay? So especially if you're chemistry majors, and especially if you're going to take PChem, you're going to want to pay close attention to this, because the motion of electrons in an atom, okay, is very strange. It cannot be described by Newtonian mechanics. You have to use quantum mechanics, and it's like the electrons are behaving more like a wave pattern than like a particle inside of an atom. And that's what those orbitals are, like the s orbitals and the p orbitals. Those are actually wave patterns that the electron forms inside the atoms. And this mathematics here, what I'm describing right now, will be a gentle introduction into the into that quantum mechanics, so the wave mechanics of electrons and atoms. Okay. So let's start off. So we've got these coupled harmonic oscillators, and they're going to be interacting with one another. And before I throw that equation at you, let's look at the equation for just one harmonic oscillator, which we did last semester. Okay, and one harmonic oscillator can be described by Hooke's law. And what it basically says is, I have an oscillator, and if it's at x equals 0, which is its equilibrium, there's no force on it. But if I displace that oscillator at distance x, then there's going to be a force on it in the opposite direction, which tries to restore it back to equilibrium. The bigger the displacement, x, the bigger the force. Okay, so when it's at equilibrium, there's no force. I displace it a little bit, there's a little bit of a force back. I displace it a lot, there's a much bigger force back, and so on. And now you could just start with Hooke's law here. Oh, and K, of course, is the spring constant. It's how stiff that spring is. It's the proportionality between how much force you get for how much displacement. Okay, and the minus sign again is the direction. You displace it to the right, the force will be to the left. Okay, so this equation is sufficient to give you all of the equations of motion for how this oscillator will oscillate back and forth. In fact, if you look at Hooke's law, you're going to say, well, I don't see anything sinusoidal about this at all. Like, where's this oscillating back and forth? Like, how is that a sine wave or a cosine wave at all? Well, you don't see it at this point, but what you do is you go, oh, Newton's second law says that the force is ma. F equals ma is the second law. And so you get ma is equal to minus kx, okay? And you still don't see it, okay, except that if you rewrite this, you can rewrite this as a is equal to minus omega squared x, and I took k divided by m and wrote it as omega squared, like that, and you know that that's the angular frequency. All right, so you write a is equal to minus omega squared x, and then you go, oh, but a the acceleration is just the second derivative of the position with respect to time. Okay, it's the rate at which the rate changes. Okay, so the rate at which x changes, that's the velocity. The rate at which the rate changes, that's the acceleration. Okay, so we started from Hooke's law right here. Okay, and we recognize that the force was just proportional to the acceleration because of Newton's second law. All right, and the acceleration is just the second derivative of the position with respect to time. And we get this equation here, which says that the second derivative with respect to time is equal to minus omega squared times the position x. Okay, and at this point you're going, this looks like it's more something that you can solve. Okay, because what it basically says is find me some function of time. Okay, it has to be a function of time because you're differentiating with respect to time. Find me some function of time such that when I differentiate it twice, I'm going to get the same function back, but with this extra factor minus omega squared in front. Okay, so let me say that again. So find some function. Okay, so x is not a number here. X is not a number. It's a function, and it's a function of time. Okay, means that there's a t variable in there. And I'm going to take that function and I'm going to differentiate it once and then again twice. Okay, and when I differentiate it twice, that's the acceleration. What am I going to get? I'm going to get the same function back again. It's like I take it, differentiate it twice, I get the same function back again, but then there's this extra minus omega squared in front. Okay, and you go, well, what kind of function does this look like? And it turns out that that function is a cosine, where the argument is omega t plus phi. I'll tell you what that phi is in just a minute, but it's basically a cosine. Okay, when I say sinusoidal, I mean either sine or cosine. They're really, sines and cosines are really the same. They're just displaced in time. Okay, and what you're seeing here is you started from something like Hooke's law, which doesn't seem to have anything sinusoidal in it at all. Like, it's not obvious why a Hooke's law will give you something which bounces back and forth like that according to a cosine. But when you realize that that f is really the acceleration, which is really the second derivative of the position with respect to time, and that second derivative of position with respect to time is proportional to the position, that's the part that gives you the sinusoidal. Okay, and so you get the solution here. All right, now what's in the solution? We looked at it last semester, but it's worth repeating because we're going to redo this, but now but for waves, for an infinity of oscillators, not just one. Okay, and so what is the solution? Well, x is the position, it's the displacement. Okay, and it's a function of time. All right, a is the amplitude. It's like how far does it get displaced, because the cosine just bounces back and forth between -1 and 1, and of course a real oscillator will bounce back and forth between some positive amplitude, negative amplitude, and so that's why you have to multiply the cosine by a. Okay, and then there's that omega, but it's multiplying t here. Okay, and when you look at this, you go, oh, that's the periodicity. Omega must have something to do with the periodicity, how fast this thing oscillates back and forth, and sure enough, it's the angular frequency. Okay, so I'm not going to go over all of that because we did it last semester, but you'll see it again also later in this lecture. So it basically says how fast does this thing bounce back and forth. Angular, so it's a frequency, but it's angular because it's got an extra 2 pi in there because it's inside of a cosine. Okay, and so omega is this angular frequency. And remember how I defined omega? Omega was actually omega squared was k over m. Omega is square root of k over m, and so the angular frequency turns out to be just the square root of the spring constant, how stiff the spring is, divided by the mass. Okay, and then this phi, I just put it in there for completeness. We didn't use it last semester, but it's basically the phase. Okay, you might say to me, well, why did you pick the cosine? Why didn't you use the sine there? And you can, and it would work out just fine. Okay, you could differentiate this twice and it would still fulfill it. You go, well, why cosine and not sine? That phi kind of smears a cosine into a sine and vice versa and everything in between. In other words, it's the phase is the point in the cycle at which the oscillator is at t equals 0. Remember, cosine of 0 is at 1. The sine of 0 is at 0. And so one of them, the cosine, is at maximum at t equals 0. The sine is at 0 at t equals 0. And you might say to yourself, well, couldn't I start at a half? Couldn't I start at 3/4 the amplitude or at some other point in the cycle? And the answer is yes, absolutely. And that's why there's the phi. Now, because you get to choose usually where you put your t equals 0, your time origin, phi is not that interesting. But if you're going to compare a couple of oscillators, the phase does become interesting, okay? And so you know that if I change that phi, like between 0 to 90 degrees, then the cosine goes from cosine to the sine, okay? And so it basically gives you a sinusoidal between cosine and sine and everything in between, okay? It's usually known as the phase. We're not going to use it in any problems, but I'm just showing you that you could put that there, and this would be a complete solution, okay, to that equation, to this equation right here. Okay. All right. So that was a bit of a review with a little bit of different emphasis on how the equations of motion for a single harmonic oscillator goes. What would it be for a wave? Like, how would you write the equivalent of that for a wave, especially since you've got an infinity of oscillators? And I say an infinity because really you can look at the string at as small as possible level. I know that ultimately you get down to the microscopics, but as far as you're concerned, there's like so many little molecules in there, and they're all acting like oscillators in that string. You might as well just say, 10 to the 23, that's pretty much infinity. Okay, you need a continuum, in other words, of oscillators, all coupling with one another. And it turns out that the wave equation is this equation right here. Okay, and it's a little bit hard to get your head around. And as I said, I'm not going to study it in depth. I just want to make sure that we have some intuition. And in the tutorials that I'll be doing later, I'll show you how to solve some problems with this. Okay, so I'm not actually even going to solve problems with right now. I just want to really understand what this equation is saying. We have this y here. Okay, let's start with that y. Y is going to be the displacement of the string from equilibrium. It's like, how far has this string been displaced from equilibrium? So if you take a look at a picture here like this, you could say, look here, see that the curve there, the sinusoidal curve, that's my string, okay? And the x-axis here, that's where it would be at equilibrium. And I could say, well, over here, how far has that string been displaced from equilibrium? And it's been displaced that distance y there like that, okay? And you can see I have the arrow pointing up because that displacement is positive. Okay, so that y1 there would be, well, if we count each one of these units, see these lines, these horizontal lines, we call them like 1 unit. So this, the top of the crest there is 2 units. Y1 would be like 1.5 units high. Okay, and over here, see y2, it's going down, it's actually negative. So at every point in the string, it's been displaced from equilibrium, and how far it's been displaced from equilibrium, we will call that y. Right here, where it passes the x-axis, that displacement is a y equals 0. Okay, so that's what y is in this equation. All right, but you'll notice that I've got the second derivative with respect to time and on one side and with respect to x on the other side. And you say, well, what is this y? What is the t and what is the x? Well, the t is time and the x, so don't confuse this with the x that we just did with the harmonic oscillator. I used x there because that's what we used last semester. But x has a different meaning right now. X is, where are you along the string? Like, how far along the medium are you? Okay, because the displacement at a given time, say t equals 0. Okay, so we're just going to take a picture of this wave at t equals 0. So you're frozen at one point in time. If you're at x1, well, then you have a displacement y1. But if you're at a different x, x2, you've got a different displacement y2. So clearly, the displacement y from equilibrium depends on where you are along the medium, and we're going to call that x. All right, so that's one of the things that y depends on. If you're at this x, you get this y. If you're at this other x, you get a different y. Okay, you can see there's a dependency on x by y. What about time? Well, this picture here was at t equals 0, but if I let this evolve like a movie, then what you would see is that this whole wave moves to the right. So at some later time, okay, I don't care how much later, some later time, the wave has moved. So you can imagine the crest that was here, has moved now to there. Okay, and so now, even at the same point x1 here, you get a different y. All right, So not only does the displacement depend on where you are in the medium, it also depends at what time you're looking at it. If you're looking at t equals 0, you've got this displacement here, y1 is positive. At a later time, same place in the string, same x1, at a later time, you've got a different displacement. You can see it's negative, okay? So this is a little hard. I think this is what makes the whole thing hard, is that there's really two dependencies on the displacement. The displacement, okay, so why is the displacement? Depends on when you're looking at this medium, the time, and it also depends on where you're looking on the medium, okay? So there's two things going on. And so this equation is very interesting because what it says is that the rate at which the rate of the displacement changes in time is proportional to the rate at which the rate of the displacement changes in x, okay? Now, I have to say rate of the rate because that's what the second order derivative is, okay? In time, when you look at the rate of change, that's the acceleration, okay? Right? Because the rate at which position changes, displacement changes, is velocity. The rate at which the velocity changes is acceleration. So the rate of the displacement is the acceleration. Okay, so remember that from last semester. It was one of our first lectures. Okay, so this side, the left-hand side, is your acceleration in this equation. The right-hand side is the side that's a little hard to see. Okay, you say, well, what is that in x? And it turns out to be the curvature, which I'll show you in a minute. Okay, and then in addition to that, there's a constant here. All right, and if I were really doing, you know, a derivation from first principles, you wouldn't know that this is actually the velocity squared. Okay, that would come out of the analysis, but it turns out that that's what it is. It turns out that the constant of proportionality between the acceleration on the left-hand side and the curvature on the right-hand side is the velocity squared. Okay, and we will see that coming out below. All right, so this is the second order differential equation. This is the equivalent of that, the equation for one oscillator, but now applied to infinitely many oscillators connected to one another. Okay, coupled, as we say in physics. Okay, and so let's see how this coupling works. Like, why are these two things coupled? All right, so let's move down here. So let me just remind you, on the left-hand side, the second derivative with respect to time, the rate at which the rate of x changes, sorry, the rate at which the rate of y changes, the displacement, that's the acceleration. That's just like with the oscillator, only there it was x. Okay, so what I'm trying to show you in this slide is that x here for the oscillator has been taken up by y. Okay, and so that is basically your acceleration. The other side, this is the side that's a little harder to see, is the curvature. So when you take the derivative of a function, you get the slope. Okay, you get the slope. But when you take the second derivative, you get the curvature. And the curvature is not like, is it sloping up or is it sloping down? That's the first derivative. It's, is it turning? You know, it's like, was sloping up and now it's sloping down. So you could take here, look here, say at a crest. So this is just a part of a wave here. I'm just trying to draw the top of the crest of a wave here, okay? There's a big curvature there. Why? Well, because at first you're sloping up, okay, on the left-hand side here, and then you're sloping down. So you went from sloping up to sloping down. That's a big change in the slope. And when the slope is changing, that's what curvature is. Curvature is the rate at which the slope changes. Okay, so you get your biggest curvature at the crest. All right, you get your smallest curvature when the wave passes through equilibrium. Okay, right there. So these might be a little bit abstract. Let me just show you up here in the picture again. Okay, so the biggest curvature happens at a crest or at a trough. Why? Well, because you see you're sloping up on this side and then you go through a zero slope and then you're sloping down. So that's a big change because you're going from positive slope to zero slope to negative slope. But when you pass through equilibrium here, you see how that's a straight line? You're sloping down before you're at equilibrium, you're sloping down after, so that the curvature didn't change very much. Big curvature at crest and trough, very little curvature when you pass through equilibrium. Okay, so having said that, what I'm trying to do here is I'm trying to get you to have an intuition into what this curvature is getting at. So if you take a look at the crest here, okay, and you say, what, just think I sort of drew this little X here, okay? And I'm just saying, concentrate on that point and ask yourself the question, what forces are acting on that point? I know there's gravity, but gravity is really not that interesting for these waves. Okay, it's really the tension in the string that's interesting. So if you were a point right here at the crest, what you would feel is a tension to your left pulling downwards and to the left, and a tension on your right pulling downwards and to the right. Okay, so if you take a look at this tension here on the left hand side, there's a component which is going to the left like that, and there's a component which is going down. And this tension on the right, there's a component going to the right, and there's a component going down. Now the component to the left and to the right, okay, that is the horizontal components, they'll cancel because there's a component to the left here, there's a component to the right there, they'll cancel. But there's also a component down, and both the tension on the right and the left have a component down, okay? So they add. And what that says is that the overall effect of the tension at a point at the top of the crest, the overall effect of that tension is to pull that point down, okay? So where there's a big curvature, where the curvature is high, that's where the tensions will tend to add up and try to restore that point back to equilibrium. You can see that, this tension on the left is pulling it downwards, this tension on the right is pulling it downwards, so that point at the top of the crest wants to be pulled back down to equilibrium. Okay, so the bigger the curvature, the more the tension tends to add up. What happens where the curvature is low? That is when the string passes through equilibrium. Well, at that point, if you draw the tensions, one tension is pulling this kind of upwards and to the right, this tension is pulling downwards and to the left, and you can see that they're like 180 degrees in opposite directions, and so these two tensions will just cancel. So wherever the curvature is low, the tensions cancel. So what is this saying? The second derivative with respect to x is actually proportional to the net force. Okay, so let me say that again. Wherever the curvature is big, so the second derivative of the displacement with respect to x, that's this curvature. Okay, wherever that curvature is big, that's where the force is big. Wherever that curvature is small, that's where the force is small, net force. Okay, so the curvature is actually proportional to the net force on the oscillator at that point x. Okay, so you can see here y, I'm actually differentiating y with respect to x. Okay, but I'm looking at a point x. Okay, so I pick a particular point x and I say, well, what's the second derivative of the string there? Okay, the shape of the string. What's the second order derivative with respect to x at that point at x? Okay, and that turns out to be proportional to the net force. All right, so I know I'm not doing this very rigorously. By the way, there's a lot of sites on the web where they do it rigorously. The reason I didn't want to do it rigorously for you is I didn't want to overdo this lecture and throw so much math at you that you lose sight of the intuition. I'm just trying to show you the overall picture of what this equation is doing. You could just go on Wikipedia for the wave equation, and they show these very similar pictures, but they actually do the math where they divide the string up into mass segments, and you'll see everything come out of that. Okay, but again, I didn't want to go there. Okay, and so now when you look at this equation, it's got a very different look to it. Okay, the part where you have the second order derivative with respect to time, that's like your acceleration. Okay, and the part where you have the second order derivative with respect to x, that's like your net force. So you have the net force on one side and you have the acceleration on the other side, and there's some constant of proportionality here, v squared. Okay, and that constant of proportionality, that's like where the mass is actually embedded in that, and so basically this is just like a F equals ma. Okay, so that is Newton's second law, but it's Newton's second law applied at every single point in the string, and also such that the curvature there is important, which is what couples the oscillator to the neighboring oscillators. And let me just make that coupling point a little bit clearer here. You wouldn't have these tensions to the right and to the left on that point at the crest if it weren't for the neighbors. In fact, these tensions to the left and to the right are precisely the effect of the neighbors. Okay, so that coupling part, the part where the neighbors are affecting the masses, that's coming in right here. That's coming into how the force is constructed. Okay, and that makes sense because if one oscillator moves up, it exerts a force on its neighbor. And what is that force? The tension, and that's encoded in that curvature. Okay, so a little bit of a hand waving argument. It's not very rigorous. Believe me, it can be made rigorous. And if you do go on in physical chemistry and you take a look at Schrodinger's equation, that you will see it rigorously done there. But this is, I think, good enough for our purposes. Left-hand side here, second derivative with respect to time, the acceleration. Right-hand side, second derivative with respect to x, curvature, and the curvature is the net force. So you basically have net force and acceleration being equated along Newton's second law, where V here is got to have the mass in it because it's F equals ma. And you go, well, where's the m there? Okay, we got the net force and we got the acceleration. Where's that mass for F equals ma? It's inside the V. It's inside the V. Okay, so if you had done a full analysis, you would have found that V comes out for the string to be the square root of the tension divided by m. Remember I said a minute ago that V has to have that m in it, the inertial quality, the mass. There it is. It's inside the mu because the mu, the linear mass density, is mass divided by length. Okay, and also there's the tension there because that's also part of that curvature. That there is a curvature, but the curvature isn't the full story. It's also how hard the points are being pulled. They're pulling on one another. Okay, how hard the masses are being coupled to one another, and that is the tension. Okay, and so the velocity here has the equation square root of the tension divided by mu for a string, where mu is going to equal the mass per unit length. In other words, the linear mass density. And this is exactly the equation that we used when we solved problems in that other lecture. Okay, this particular form actually turns out whenever you analyze any waves, like I've been talking about waves on a string, but if you analyze, like, say, waves in air, you get the same kind of equation. You get that the velocity of sound, because that's what waves in air are, they're sound. It turns out to be the square root of the bulk modulus divided by the density of air. Okay, and you see, hey, that looks an awful lot like this. Okay, and that's right, because the bulk modulus, and remember what the bulk modulus is when we looked at the elasticity, it's how much you can compress something. Okay, it's the compressibility, the bulk compressibility of an object. Okay, or in this case air. And so this is kind of like the tension and not a linear mass density, because air is not a line, it's not a one-dimensional object, it's a three-dimensional object. And so instead of a one-dimensional mass density, you have a three-dimensional mass density. Okay, and in general, whenever you apply that equation to any wave phenomenon, you always get that the velocity is equal to the square root of something that measures the stiffness, like how hard it is to deform the material. Okay, and that'll be the top part divided by something which measures the mass density. Okay, and remarkably, this same equation comes out at the very end of the course. You'll see this equation even comes out for electromagnetic waves. And electromagnetic waves are like light, visible light, infrared. Okay, let me go through them in order. So at the very low end, you've got radio waves, and then you get microwaves, and then you have infrared, then you have visible light, and then you have ultraviolet light, and then you have X-rays, and then gamma rays. Okay, so there's the whole spectrum of electromagnetic radiation, electromagnetic waves. Okay, and it turns out that there's a velocity, the speed of light. Okay, and the speed of light, remarkably, turns out to be a formula that looks very much like this, only instead of the stiffness and the mass density, what you get is a measure of the ability of space to sustain electric fields and the ability of space to sustain magnetic fields. Okay, and so electromagnetic waves are exactly that. They're waves in electricity and magnetism, and even there you get a formula that looks very similar to this. Okay, because it's always the same equation. So this equation, which we had way at the beginning here, right there, okay, that equation right there, applies to any wave phenomenon, okay, that you like. All right, whether it's waves on a string, waves in air, waves in electromagnetic in a vacuum through electromagnetic propagation. Okay, and so there you go. All right, so again, I wouldn't say this was a true derivation. This was more like just giving you a sense of what's going on and how you can actually derive wave phenomena, all of the wave phenomena, from Newton's laws, which is rather remarkable. Okay, last thing I'm going to talk about and theoretically is, oh, sorry, not last thing. Two more things. One thing is, what do the solutions to this equation look like? Okay, and I'm not going to do any problems right now, but we will. We'll do some problems in the tutorial section. I'll show you what kind, because people will ask, well, what kinds of questions could you ask, and you'll see that. All right, but the solutions to that equation, they have some sinusoidal form, so they look like the solutions to the simple harmonic oscillator. A is equal to y is equal to a cosine omega t. But then there's an extra part. There's a minus kx in there in the argument, and you wonder, why is it both time and x? Okay, t and x, and the answer is because there's two things oscillating. There's an oscillation in space, and then there's an oscillation in time for any one point. And so if you take a look at the displacement at any given point in the string, there's your x right there, and at any given time, okay, that is going to depend on both the time and the position, and it's sinusoidal. It's sinusoidal in both time, and it's sinusoidal in x as well. Okay, and so what it looks like is y is equal to a cosine omega t minus kx. Okay, by the way, it could also be plus kx there. It just depends whether the wave is moving to the left or to the right. Okay, what I have there is a wave that moves to the right. Okay, now we know what omega is. All right. Omega is basically the angular frequency, all right, and it's equal to 2 pi over capital T, where T is the period. It's the time for one complete cycle, all right. And what that is, what this one complete cycle is imagine that you're a point on a crest. What are you going to do in time? You're not going to move with the wave. You're going to stay in place, and you're going to just oscillate up and down. So how long does it take you to go from crest down to trough and back to crest again? In the same place, okay, because you're not moving an x, you're just a point on the string, and that is time t, okay, of the period. And so this omega here is the angular frequency. It's just 2 pi over capital T, where t is the time for this complete cycle for any point in the string. All right, but what's this minus kx? By the way, that k is not the spring constant. Okay, so unfortunately, in physics, we have a lot of symbols which are duplicates because there's a lot of things to give symbols to. This k here turns out to be what's called the wave number. Whoops, let me scroll down a bit. Okay, it's what's called the wave number. So that k is the wave number. Okay, not to be confused with the spring constant. Well, just like omega was 2 pi over capital T, where T was the periodicity in time, k, this wave number, is 2 pi over lambda. And what's lambda? It's the wavelength. It's the periodicity in space. Okay, so it's like how far do you go from one crest to its neighboring crest? Just the periodicity in space. So k is exactly the equivalent of omega, but spatially rather than temporally. All right, and t, the period, you can think of the periodicity in time. Lambda, the periodicity in distance. Okay, omega is going to be the frequency of that periodicity in time, and k is the I don't want to call it frequency, but the rate of the periodicity in distance or in space. Okay, so both of them are kind of analogous to one another. Now, this is the part that I'm not going to do for you right now. We will do this in some problems. If you substitute this a cosine omega t minus kx into that wave equation, it solves it. You get a solution. Okay, and part of the solution that you get is that omega and k are not independent of one another. They're actually related, and they're related by this form right here. Okay, and again, you'll see this come out when we do problems. Okay, so both in the assignment and in my little tutorial that I'll have in addition to this, you'll see how this pops out. Okay, so omega, the angular frequency, is going to equal the velocity times k, the wave number. All right. Now that doesn't look familiar, except that if you write omega in terms of the frequency f. Now above I had it in terms of t. Okay, so I didn't write this, but I probably should have. So omega is equal to 2 pi over capital T, but you could also write that as 2 pi times f, where f is the linear frequency. Okay, so if you write omega here in terms of the linear frequency, so omega, write it as 2 pi f, and k you write as 2 pi over lambda, and then the 2 pi's cancel, and you just multiply throughout by lambda, you get this here. Okay, and this is the equation that we started the last lecture with, which says that the velocity on a string is fixed because of the medium, because it has a certain linear mass density and it has a certain tension. That's it. V is fixed. But lambda and F are not fixed, but they're not independent of one another. If you make lambda bigger, the frequency has to be smaller, and vice versa. Okay, so small frequency, big lambda. High frequency, small lambda. Okay, and so they very inversely proportional to one another, and that's because V simply has to remain fixed. So in substituting this solution here, a cosine omega t minus kx, into the wave equation that I gave above, you will get a solution coming out, and that solution will insist that this be true, which is basically just this. So that's one of the first things that comes out of that wave equation, is one of the equations that we used in that other lecture. Okay, so you can see how you can derive a lot of things. A lot of the properties that I just sort of threw at you in the last lecture, you can actually prove them out of the wave equation. Okay, and this brings us now to the last point. I'll skip this part because I actually went over it in the other lecture. Oops, one more. The last point we'll go over is superposition. Okay, and this is yet another thing that comes out of the wave equation. Okay, and what superposition basically says is that if you have two different solutions, like above I said a solution to the wave equation, you say, well, how many different solutions can there be to the wave equation? An infinity of them, actually. You can have all sorts of different solutions, okay, by varying the amplitude and varying the frequency and k. Okay, omega and k can vary as long as they're locked. Omega and k are locked together in the correct ratio to give you the correct velocity. You've got a solution. And so you can see that you've got an infinity, because you can vary any omega and corresponding k and you'll get a solution. You can also have an infinity of different amplitudes. So there's a whole bunch of different solutions to that equation. Okay, so suppose we have two such solutions, y1 and y2. So they're both solutions to that equation independently of one another. If you add the two together, guess what? The sum of the two is also a solution. Okay, that's not always true of all equations, of all differential equations, but it is of this one, and that's important because it says if you've got one wave and you've got another wave and they're propagating on a string and they meet, they just act like a wave. The sum of the two waves acts just like a wave. Okay, and I can show that here. I could first show it to you mathematically and also show it to you graphically. Why does that work? Well, imagine that you have y1 and it's a solution and y2 is a solution. Well, if you take the second derivative of the sum of the two, the second derivative just distributes over the two. And so you've got the second order derivative with respect to time of y1 plus y2. That's just the second order derivative of y1 plus the second order derivative of y2. Okay, this is the fact that this follows from the fact that the derivative distributes over addition. Okay, now that's true not only of the second order derivative with respect to time, it's also true of the second order derivative with respect to x. And so both the on the left hand side and on the right hand side, the operator, the differentiation operator, will distribute. Okay, and since y1 is a solution and y2 is a solution, the equality holds. Okay, the equality doesn't fall apart. I'm not going to do that right now because again, you'll do that as part of our problems. Okay, but if this is true, that means that if I have two waves, okay, and they're coming at one another. Now I didn't draw the full waveform. I just drew two crests here like that to not make this too complicated a picture. Okay, and you'll notice that each crest here has a height of 1 unit. Okay, taking these horizontal lines here, say, is 1 unit. So this crest has a height of 1 unit, and this crest has a height of 1 unit. Well, that's the displacement. Why? Okay, as they come together, what happens? They just add. Okay, the dynamics of the two waves continues as the wave equation would predict, but they just add one on top of each other. Okay, and so here they are. I'm trying to show like an evolution here. Here are the two crests far apart, and here they are coming together, and they're starting to add one another. And then when we're right on top of one another, it's like 1 plus 1 here, and you get a height of 2. So the two crests will simply augment one another and you'll get a height of 2. And then they'll still continue, these two crests here, they'll just continue, that one and that one, in their original direction because they're acting as if they're independent of one another. They're adding as they go through one another, but they're acting independent of one another in their dynamics. And so here they start to come apart, and then they just come apart like that, and then they retain their original height. Okay. Now here I showed the two as being the same height, but I could have made one bigger than the other. And then, if the bigger one, say, was on the right-hand side here, then the bigger one would have been on the left-hand side. It's like they pass through one another as if they weren't even there. And when they were on top of one another, they added. Okay. So the same is true for a crest and a trough. Okay. And so here you got a crest and a trough, and as they come together, they add. But now this crest has a height of +1. That trough has a displacement of -1. So +1 and -1, when they sit on top of one another, +1 and -1, they cancel. Okay, the energy is still there, so it's not like that wave disappears. They meet and they annihilate forever. The energy is still there, and so then they just start to come apart. And the crest will continue to the left, and the trough will continue to the left, and the crest will continue to the right. Okay, but when they were on top of one another, they added. Okay, that's the principle of superposition. And the reason I went over this is because all of those properties that I talked about in the previous lecture, like remember we talked about beating, okay, and we talked about standing waves, and then reflection, refraction, diffraction, and interference. Especially with interference, I think you can see what's going on there. All of those can be explained in terms of this principle of superposition, and superposition comes directly out of that wave equation. Okay, so those phenomena that I just sort of threw them at you. I gave a little bit of an explanation of how they came about, but I didn't really derive them, and I'm not going to derive them even here. Okay, but I think you could see how, like, if you make use of superposition, well, definitely you get the interference, because remember what interference is. When you have two sources that are emitting waves, whenever you have a crest from one wave meeting a crest from another wave, you get an extra big crest. And trough from one and trough from the other, you get an extra big trough. And whenever you get a crest and a trough meeting, they tend to annihilate one another. That's precisely the the principle of superposition. But it's not just an interference, it also happens with diffraction. That's the bending around corners. There it's a little harder to see. You say, well, how does that happen? How does that work? Well, I'll skip it. But if that's what this Huygens principle that I mentioned, if you just make use of Huygens principle, which comes out of superposition, you'll get the same kind of effect there. Refraction also, okay. A little bit harder to see because you need to join together two medias, one with a V1 and another one with a V2, and so on. All of those will come out of superposition, and more generally out of the wave equation. Okay, so this was a little bit of a deeper look into the math behind the wave equation. At this point, you're going to say, well, what kind of problems can you ask? For this lecture, just make sure that you understand the principles, and I'll show you, the kinds of questions. You'll see them in your assignment, and you'll also see them if you want to sit in when I record that tutorial. You can sit in and you can see it, or when you watch it afterwards, because it'll be recorded and you can watch it afterwards. You'll see how I solve some problems making use of that wave equation. It does require you to know how to differentiate sines and cosines. Okay, we did that last semester. You should have done that in your calc, and so that's the only mathematically demanding thing. Okay, so that's it for this lecture, and well, thank you for listening.